on to whatever today's notes are, why don't I start with just two basic examples of review, and I want to show you a couple of ways we can approach this. Here's the two types of ways that we could be asked to solve things involving sine, cosine, and tan, stuff like that. Here, I'm going to tell you sine of x equals 7 over 9, and here I'm going to tell you sine of 7 pi over 4 equals x. You guys see the two locations where the variable could be? Here, what am I asking you to solve for? You're not phrasing that very well. This is an angle. Does that make sense? Here, I'm asking you what angle gives you 7 over 9. And then here, I'm giving you an angle, and I'm asking you, tell me what its ratio happens to be. So let me walk you through how to kind of solve both of these things here. And then I'm going to try to do it two different ways. One way I'm going to do it is using the unit circle. And then the other way I'm going to do is using the little manipulative that we just made yesterday that some of you have. We'll make one for you too in a little while. So let's start with the first example here, sine x equals 7 over 9. So sine x equals 7 over 9. So here's one option. You could use the unit circle. Option number 1, use a unit circle. And this is what we would have done before we left for Easter break. I would have said, well, let's plot this somewhere on a grid here. Now, what is sine supposed to be equal to in terms of like its ratio? Yeah, and we've also hopefully learned that that could be the y value over the radius as well. Those are both valid things. So I need to figure out where can I have a y value which is positive and a radius which is positive. And we would have learned a quick little nifty rule, the cast rule. That's not right. The cast rule starts in this quadrant, C, A, S, T. And then we could say, well, sine could be positive in this quadrant here, or in this quadrant here. And then if I want to do my opposite, yeah, totally. Opposite over hypotenuse and opposite over hypotenuse. That seems to fit in those quadrants. How many answers are there to this? How many angles are there that could make this 7 over 9? Seems like 2 should be the right answer, but it's not. Well, it's the same reference angle on both ones, but there's actually an angle that could go from here to here that would work. There's also an angle that could go from here to here that could work. So you might think 2, but that's actually not correct because, well, what if you went backwards to there? That also works. What if you went that way to there? That would work. What if you went around the circle 400 times and then stopped here? So the unit circle kind of helps, but another way of solving this is to know what a sine graph looks like. What we learned last day is that a sine graph starts here, goes up, down, and like that. We're making that little manipulative that Jamie has in front of her there. But what's the problem with that little section there is that that only shows one little snippet, one wavelength, so to speak, of what a sine graph looks like. This thing repeats itself ad nauseum for forever. And it really does that here and here as well. So this would actually be option 2. This would be knowing what the graph looks like. So let me continue on with the graph section. I want you to tell me where the sine graph is equal to 7 over 9. How tall does the sine graph get to? What's the highest that this value gets to? 1, yeah. Hopefully you'd agree then that 7 over 9 is less than 1, right? It's not a lot less than 1, but it is. So 7 over 9 might be right about here. Well, look, there's an answer here and an answer here. And along this axis, this would be like the angle that it could be. Well, that kind of corresponds to my unit circle where there's an answer here, but there was also a second answer in that quadrant. Does that make sense? But I could go around the circle again. I could go all the way around the circle once and land here, all the way around the circle once and land here. Well, that would be this spot and this spot, and then this spot and this spot. I could even go backwards around the circle and get some negative angles. See how that kind of corresponds? Now, the two ways I would solve this then with my calculator would be like this. One option, I'll just do this in degrees just to keep it simple for right now, because we'll do radians for the next one. If I were to try to inverse sine 7 over 9, it's going to give me an answer. And what your calculator did is it found the closest answer it was able to find, which was 51 degrees. Does 51 degrees make sense up here? Well, I think so, because that right there is probably 51 degrees. So there is one answer that would work. But how do I apply that 51 degrees over here into this quadrant? What do I do? Well, that's 51 degrees. So how far is it from here to there?
180
Yeah, 180 minus 51, which would be 129 degrees. Now let's check that. If I were to type in the sine of 51, let's say, yeah, that's basically 7 over 9, minus a little bit of a rounding error. But is that the only angle that would work? Why don't we try the sine of, what was it, 129 degrees? That one works as well. Are there other angles that could work? Sure, why not the sine of 129 degrees plus 360 times 8? What does that mean? Before finishing on the 129 degrees. And look, it also is basically 0.77 repeated. So that's one option. If you get your unit circle concept, if you just inverse sine or inverse cosine, that'll get you an answer. But there's another option that I wanted to start showing you yesterday, which is, why don't we graph this thing? If I were to graph it and type in sine of x, and then see where it equals 7 over 9, a couple of things I got to do first. So I got to make sure my table fits. So when I go to my window size, I'm going to make it go from 0 to 360. Why from 0 to 360? That's one rotation around the circle, right? And then y min to y max, I'm going to make it go from -1 to +1. Make it go from -1 to +1, because that's how high the graph goes. And if I do that, this should give me the graph that you guys just made right there that goes up and down once. And then here's where it is at 7 over 9. See how it intersects twice? Well, what you could do is, if you don't like this unit circle stuff, you could graph it. You could go second calculate intersect, and you could find where it crosses. Well, it crosses many times. Here, it crosses at basically 129 degrees. Exactly like I predicted the other way, right? I won't bother finding it, but hopefully you'd agree that one there's got to be 51, right? But are those the only two places this graph will cross? Well, no, because it would cross over here and over here as well, implying that it goes around the circle multiple times. So what I'm trying to show you with the first two lessons and now the second two lessons is, one option is use the unit circle. But you have to use like some really good reasoning and common sense, because when you do the inverse sine button on your calculator, it gives you one answer. And there's not usually just one answer. There's often two answers when you go around the circle once, or if you're allowed to go around the circle more than once, there's a million answers. There's infinity answers. That makes sense? Option two, if you know what the graph looks like, you can just find where it intersects. That might be easier as well. That makes sense? Okay. The other way you could solve it right here is I could ask you for something like this. When is sine of pi over 4 equal to x? Now this one's a bit different here. In terms of a graph or a unit circle, the unit circle, there's not like 2 or 3 different locations on this. Sine of 7 pi over 4 is very specifically right here. This would be your first quarter, your second quarter, your third quarter, fourth, fifth, sixth, 7 quarters of pi. That is very specifically telling you which quadrant it lies in. Right? So there's not 4 different triangles or 2 different triangles it can be in. It's very specific. It's only around the circle just to here. What would the little reference angle in the corner be if it's 7/4 of pi? What's the last little bit left over?
45.
1/4 of pi, which is 45. Well, then the expectation would be you should have a 45-degree triangle memorized, which would be a 1, 1, root 2, except that's going to be -1. it's going downwards in the negative quadrant. And then last step, well, what is sine supposed to be equal to? Well, you just said it. Well, it's right down here. Sine is equal to opposite over hypotenuse, or y over r. So your y value would be -1, and your radius would be √2. Now let's prove that in the calculator. If I were to do -1 divided by √2, there is my answer. And then if I were to type in sine of 7 pi over 4, and remember to go to radians, because I was in degrees. Makes a difference. So I have the same thing for both of them. So the reason I want to point that out is that in this method right here, when you solve for x, if I ask you how many answers of x there are, the answer is there's an infinite number of x's. You could go around the circle 5 times. You could go backwards around the circle. But there's probably at least 2 answers in your unit circle, so you have to be very specific in this method here which one you're looking for. On this one right here, there's just 1 answer. And then I could actually also use this with the graphing calculator. I could go to, like, say, my mode. I could put it in radians. And if I go to my window, rather than going to 360, I'm going to go to 2 pi. Why would I stop at 2 pi? It's also a full circle, right? And look, the graph actually looks the exact same as before, only the difference here is rather than trying to intersect it like this, I'm really looking for when the value of x is 7 pi over 4. And look, 7 pi over 4 is in this 4th quadrant, which is what I was expecting, right? This over here would be quadrant 4. And look, it was that -0.707 number, which was -1 divided by √2. So this kind of helps put together like the 2 halves of the coin. So one side is knowing how to do it with the unit circle, which is like what I'm doing right here. The other part is knowing what the graphs look like. So yesterday we spent a lot of time working on sine and cosine graphs, which is how we made this manipulative here, which will kind of help visualize. Today I've got a very, very brief lesson. Okay, there's not a whole lot I need to do other than I want to show you the remaining 4 graphs so that you know what they look like. And then after that, I just want to do a whole bunch of practice questions. So let's look at the graphs. On my first slide, I want to point out that sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. So we're going to talk about tan. Tan is going to be opposite over adjacent. The y value divided by the x value. Now, in these ones right here, you know how the hypotenuse was like your radius? What was the radius of our unit circle always? The radius of our unit circle was 1, yeah. Well, you can always divide by 1. That's not a problem. But what happens if we have y over x? What happens if your y value or your x value happens to be 0? It could cause some problems, right? Because it was possible for your x value to be 0, and it was possible for your y value to be 0. So it actually causes an issue where this guy down here at the bottom can't actually be 0. Let me show you a little proof here. If sine is y over r, and cosine is x over r, you guys see how like the r's could cancel here, and it would leave you with y over x. There's actually a rule in trigonometry, which is the first identity I need to show you, which is that tan is actually sine divided by cosine. Tan is actually what happens when you divide sine by cosine. So if you can see here how this radius and this radius cancels, leaving you with y over x. Well, y over x is actually tan. But it causes a problem then, because the bottom of this fraction here, or the bottom of this fraction here, the bottom of this fraction here, they can't be 0. So it actually creates a lot of asymptotes in the tan graph, and this is what tan looks like. So let me show you the tan graph. What ends up happening is it goes like up, hits 0, and then goes tall again. Jumps back down to the bottom, and zips up along these lines. This is what a tan graph looks like. And the reason why you have a problem with the tan graph is that tan is supposed to be equal to your opposite over your adjacent. Let's talk about a unit circle here. Right here at 0 degrees, well, let's actually not do opposite over adjacent. Let's do y over x, because that also works. When you have 0 degrees, how much y value do you have? How high does this thing go up? 0. So 0 divided by 1 is 0. That actually explains why right here you're at 0. But let's say that you rotate this thing slowly but surely, and eventually you get to 90 degrees. What happens at 90 degrees? How much y value do you have? How much x value do you have? 1 divided by 0 you can't do. Make sense? Because 1 divided by 0 can't happen. It actually creates an asymptote right here at 90 degrees. 90 degrees, by the way, is half of pi. Well, then let's go over to here again. Let's say you're sitting over here on this spot. How do y and x compare to each other at 180 degrees? Well, your y value is 0 again. Your x value would actually be negative 1. That doesn't really matter. So 0 divided by negative 1 gives you a 0 again. What ends up happening is this graph is basically an alternating section of, if I were to graph it, it actually goes 0, asymptote, 0, asymptote, 0, asymptote. And in the middle, it basically does like a little whoosh. And this is what a tan graph looks like. I steal yours here, Jimmy. Tan is sine divided by cosine. So take a look at this. Sine is 0 divided by 1. 0 divided by 1 is 0, which is why tan of 0 is 0. Right? And again, if you go to a calculator and try typing it in, tan of 0, tan of 0 is 0. This 0 divided by this 1 is 0. But if you go over to this section right here, tan of 90, it would be 1 divided by 0. You can't do 1 divided by 0, which explains why when you do tan of 90, or in our example here, I'll do tan of pi over 2, calculator is going to give you an error because there's an asymptote there. So if I can, let's talk about some of the properties of this graph now. What was an amplitude from yesterday? Yeah, but it has to be periodic in like an up and down wave sort of format for it to have an amplitude. This graph does not have an amplitude then, because it literally goes from as low down to negative infinity as high as positive infinity. So there is no amplitude. It doesn't apply in this scenario. What is a period? How long it takes to repeat itself. Now, what's the normal period of a sine or cosine graph that we learned from yesterday? How long does it take for a thing to go all the way around a circle? 360. But look at this one here. This is a bit different here. Here's the first spot I have right here at 0. And then here's the next spot that I have that one again at pi. Well, pi is 180. And the next one over here at 2 pi is 360. So this one's actually got a bit of a different period. Tan graphs actually have a period of either 180 degrees or pi. So tan graphs actually have half the period that a sine or a cosine graph has. Okay, domain and range. Domain is the x values you're allowed to use. Are you allowed to use all the x values? So let's talk about the exceptions. Which ones can you not use? You can't use half of pi. You can't use 3.5 pi. You can't use 5.5 pi. You can't use 7.5 pi. So it's probably better to write the exceptions. X cannot be pi over 2 n. You can't have multiples of pi over 2. You see how that pi over 2n kind of covers all of them? And maybe it's even better to write it as plus or minus pi over 2n. Because you can't have the first pi over 2. You can't have 3 over 2 pi. You can't have 5 over 2 pi. Actually, does that work? Because if n is... No, that's not quite going to work there, because if n is 1, that's 1/2 of pi. But if n is 2, that would be pi right here. So I need it to be... Let's write that differently. Oh, let's do this. Let's do x cannot be pi over 2 plus or minus pi n. Let's try that and see if this makes sense to you. it can't be pi over 2, which is 90. That's where you have your first asymptote right here. The next problem you have is a full pi away. The next problem you have from there is another full pi away. But you can go backwards or forwards by any number of like pi and find a problem. We'll follow that. Okay. What about your range? What sort of y values can't you have? Actually, you can have all y values. Look, this graph goes from negative infinity all the way up to positive infinity. So actually, your range for this graph is everything you want it to be. Okay, what about your x-intercepts? How many x-intercepts do you have? Infinity. You have an infinite number of x-intercepts because you have one right here. You have one here, you have one here, you have one there, you have one there. So we need to try to find a way to write out all the x-intercepts. Any thoughts? Give me a y-intercept. Give me an x-intercept. Where is it? Pick one of them. Where's a y? Where's an x-intercept we have? That'll work. Pi. Okay. Now, where's the next intercept? How far away from pi is it? N pi. That'll work. Yeah. Let's add pi times n. So what this would mean is that you have an intercept at pi, but you can add another pi, so then you can have 2 pi, or 3 pi, or 4 pi. Does that make sense? And then the subtract just means you could go backwards. So you could go backwards pi, making it 0, or negative pi, or negative 2 pi. Okay, what about your y-intercept? Just the one at 0. Yeah. And then I should point out here, your asymptotes are really the same thing as your domain. Your asymptotes are all the problem spots, right? All the spots where you had the dotted lines on. That's what a tan graph looks like. Right, for the next ones here, I'm just going to show you what the graphs are, and we'll talk through the properties here. This is a graph of cosecant. Remember cosecant? Cosecant is what happens when you flip a sine graph upside down and take its reciprocal. I want to do this fairly quickly because I don't want to spend too much time. This is equal to sine of theta, but like it's 1 over top of. It's where you take its reciprocal. Look at this point right here. What's the y value on the red graph right here? What happens when you do 1 divided by 1? Still 1. See how that's on both graphs here? What's the y value right here? 1 divided by a half gives you 2. What's the y value right here? Let's call it a fourth. 1 over a fourth gives you a y value of 4. But here's where it gets really challenging. What happens right here where you have a value of 0? What's 1 divided by 0? Can't do that. Hence, there's actually an asymptote here. So just to make sure it's clear, this red graph in the middle is not the graph we're looking for. The graph we're actually looking for is basically a series of alternating u's, where it goes a positive u, and then a negative u, and a positive u, and then a negative u. That's what a cosecant graph looks like. So if I could draw that again here, it basically goes like this, and then like this, and then like this, and then like this, like this, and like this. That's what a cosecant graph looks like. So let's talk about the properties here. What's the amplitude of the cosecant graph? Actually, it doesn't have one. It's not a up and down sort of function in the same sort of way. That doesn't really work. What about its period? How long is it going to take to repeat itself entirely? Pick a point, like say this one right here. How long does it take to get from this point to this point right here? How far distance-wise is that in the x direction from here to here? Yeah, about 6.28 actually. It's 2 pi. It's the same period as a sine graph, right? How long would it take a sine graph to get from here to here? 360 or 2 pi, right? So it's actually the same thing on this one here. Your period is still 360 or 2 pi. However, in your domain, you still have some issues because it goes asymptote, curvy section, asymptote, bottom curvy section, asymptote, over and over like that. So your domain, again, has issues. Probably the first asymptote would be like, say, right here at 0. But you have an issue every, well, let's say, pi n. These are the numbers that you can't have. You can't have 0. You can't have pi. You can't have 2 pi. Why can't you have 0, pi, and 2 pi? Well, look at this. Here's your sine graph. Here's 0. 1 divided by 0, can't do. Here's another 0. 1 divided by 0, you can't do. Well, look, that was at 180, which is pi. Here's another one. You can't have those ones there. See how, like, this guy has asymptotes here, and here, and here? Well, now look at what cosine's graph is going to be. It's actually on the next slide here. Cosecant, its reciprocal is secant. Check out where its asymptotes are. It actually is good right to the middle of the graph, but then it has asymptotes alternating here and here. The reason for that is that the cosecant, the cosine graph, has zeros on the alternating sections. Remember how yesterday I kind of pointed out how it was like how a clock kind of either chimes on the hour or on the half hour? Sine has zeros on the 0, the 180, and the 360. So therefore, cosecant has asymptotes on the 0, the 180, and the 360. Cosine has its zeros on the 90 and the 270s every half hour increment. If that makes sense. Therefore, this one has its asymptotes on the 90s, the 270s, every other alternating one. So these two graphs here are almost identical to each other again. This page. Here's cosecant. It starts with an asymptote and then it goes top, bottom, and alternates a section, an asymptote, a section, an asymptote. This one right here actually has like a U right through the middle of it and then goes asymptote, section, asymptote, section. Make sense at all? Okay, last one. This is what cotan looks like. Cotan looks very similar to tan, only rather than being an uphill sort of graph, if you guys look back at your tan graph, tan, as I showed you to start class, goes like with an uphill trajectory. Cotan actually goes with a downhill sort of trajectory. And it has the exact same sort of things. It has asymptotes every like other section. Okay. The thing I need to point out for cotan is that its period is back to being pi. From here to here is 3.14, which is pi. So, big takeaway from today: sine and cosine repeat each other every full circle. Tan repeats itself every half circle. Let me show you why. And then we'll do our diploma questions. How you have like a triangle right here where you have like an opposite over adjacent. And you would have, say, let's just make this 3, 4, and 5. Tan of this angle right here would be 4, it's not opposite over adjacent, opposite adjacent, would be 4 over 3. Does that make sense? You know, the next location that you could have it would be over here, though, where you'd have a -4 and a -3. But what happens when you have two negatives? They cancel each other out. From here to here is 180. Then from here to here back again is another 180. And then from here to here is 180. Tan is always in these two quadrants here if it's positive, or in these two quadrants here if it's negative, which means it's always a half circle away from each other. Does that make sense? I guarantee tan is always a half circle. Whereas sine or cosine, sine could be in these quadrants right here, but it means that you have to go like all the way around the circle to get back to here, or all the way around the circle to get back to here, but there's really not like a link from here to here, because from here to here is a different distance than the rest of the circle. I'm really making myself clear on that. Tan, from here to here, is the same distance from here back to here. Is the same from here to here, the same as from here back to here. It's always like the same that way to that way. Sine and cosine don't have the same sort of issue. From here to here is not the same distance the rest of the way around the circle. So sine and cosine, long story short, period of 2 pi, tan period of pi. Okay, let's try some questions. So now that I've shown you some stuff, let's do these to the degree. Equation of a trig function is this. Let's find the range of the function. What does a normal sine graph look like? We got one here. What does a normal sine graph run between? Normally run something like this. It goes as high as 1, as low as -1. How long does it take for it to repeat itself? Yeah, or let's go 2 pi. If it's okay, I want to go with 2 pi because I see a pi over 3 sitting inside here, which seems to somehow indicate which one to go with. So, okay, let's talk about what these things would do to the graph. What would the minus pi over 3 do to the graph inside the brackets? What does a negative sign inside the brackets here do? Which way does it? Slides it that way, right? Because what this is x minus 2. This would be like an x minus 2, which slides it 2 units that way. Only it's not minus 2, it's f minus pi over 3. So we're going to take this whole graph here, and we're going to slide it a little bit that way. How does that affect the range of the graph? If I slide it to the right. It doesn't affect it at all, actually. Okay. What about this minus 3? What does a minus 3 do to the graph? Yeah, moves it down 3. So now my graph would be like somewhere down here. Would that affect the range? Yeah. The range is now 3 units less than it used to be. Last thing, what about this k value here? Now we don't actually get to know what that number is, but what does a k value, what does a value in this location do to a graph? Stretches it taller, right? If the k value was right here, inside, like the brackets there, that would stretch it side by side. But in front of the graph, this is the amplitude. So normally the graph goes from 1 down to -1, but this is going to make it k times taller. So it's actually going to have gone from k down to -k. Makes sense? It would have gone from 1 to 1, but whatever this k value does to the graph, it's going to make it go as high as k and as low as -k. If this was a 5, it would make it go from 5 to 5. But don't forget, then we made the whole thing go down 3. So then this is going to go down 3, and this is going to go down 3 more. So the lowest value we're going to have is -k, -3, which is written in a different order right here. Here is -k and -3. Whereas the highest value that I'm going to have, k minus 3. It got written in a different order, but do you see how right here you have a k and a minus 3? Follow that? It's challenging because you can't really type this in your graphing calculator. You really have to know like your theory behind what's happening. Let's try another one. I'm just going to do a lot of examples today. The graph of y equals cosine theta plus pi over 2 is identical to which of the following graphs? Here's one option. You could just type all 5 graphs in your calculator and see which one looks the exact same. That could work. What does a normal cosine graph look like, though? Yeah, starts at 1 and goes down like this. What would this plus pi over 2 do to the graph, though? Moves it left a little bit. It moves it left by pi over 2, which basically means that this point right here starts here. This point goes over to there. This point comes to here. Basically, it shifts it back a little bit. See how I've slid this thing back a little ways? Okay, now I need to look through this. Is that a negative cosine graph? Well, what does a negative in front of a cosine do? Negative in front of the whole cosine would flip it upside down. Well, in green here is my cosine graph. If I flipped it upside down, you kind of visualize this, then that would actually make it start down here and go up. That's not the graph I want. What does a negative sine graph mean? It means take a sine graph and flip it head over heels. Here's a sine graph. It normally goes up and then back down again. If you flip it upside down, wouldn't it go down and back up again? Isn't that what I drew in red here? Isn't this a sine graph that normally goes up and back down? But rather than going up first and back down, it's actually going down then back up again. So this is actually the correct answer. Makes sense? Another one. Cotan of 4 pi. Or sorry, 4 theta. So first, let's talk about what a cotan graph looks like. We just did it a little while ago today. A cotan graph looks something like this. It goes whoosh, whoosh, whoosh. That makes sense, folks. And basically, it has a whole bunch of asymptotes kind of in between. That's your basic cotan graph. Okay, I didn't actually write it out in our example, but where would all the problems occur in a cotan graph? Where's your first issue? What's the first number you can't type in for theta? Where's that first asymptote located at? Actually, 0. Yeah, good catch, right? And if you don't know, then just maybe type it in your calculator real quick. Let's just try the cotan. Let's try the, okay, now you can't type in cotan, so you'd have to do the tan of 0 and then make it go to the -1. See how it gives you an error? So apparently we can't do that one. So, okay, so that's your first issue here at 0. Where would the next issue have been? What's the next asymptote going to be? How long did it take a tan graph to repeat itself? Pi. Yeah, 180. So your next issue would have been at pi, and then at 2 pi, and then at 3 pi. That's where all your issues would have been. And you can kind of go back to this graph if you need to go look it up again here, but this was your cotan graph. There was a problem at 0, there was a problem at pi, there was a problem at 2 pi. On the hour, there was an asymptote. But then back to our question here. That's what a regular cotan graph would have looked like. But now we have 4 pi. What is that 4 going to do to a graph? Squished. Like this. The 4 will squish everything in this way. Okay, well, what that's going to do then is all of these are going to get squished in and in and in by a factor of 4. So your first asymptote's not going to be at pi, it's going to be at pi over 4. And your second asymptote's not going to be at 2 pi, it's going to be at 2 pi over 4. And then your third asymptote is not going to be at 3 pi, it's going to be at 3 pi over 4. Which one of these answers right here best indicates where all of my issues are? A. Because A basically says you can have any number you want, but you cannot have any increment of pi over 4 in the positive or negative direction. Right? That's kind of how this notation works. Is pi over 4, 1 pi over 4 doesn't work. 2 pi over 4 doesn't work. 3 pi over 4 doesn't work. Negative pi over 4 doesn't work. 0 pi over 4, which is 0, doesn't work. Make sense? Two trig functions are graphed below. We want to find the relationship between the graphs at point A. Okay. You can see how A is on both graphs. It's definitely on the solid graph. It's also on the dotted graph. That make sense so far? If you plug in a k value, it seems to give you back m. What you could do then is you could say that f of k equals m. Logic makes sense? If you plug in whatever this x value is to the f graph, it gives you back m for its y value. What happens if you do g of k? What does it give you? If you plug in k to the f graph, it gives you m. If you plug k into the g graph, it gives you m. Which kind of makes sense because that's where they cross, right? If you plug in k onto either graph, it gives you m. Okay, let's look through these statements, see what we can use here. Is f of x equal to g of a? Okay, well, f of x would be an unknown x value. Capital A is like a coordinate point, like say, well, it's actually a coordinate point km. Capital A isn't even a value that makes sense because it's just the letter used to represent the point, so that doesn't really make sense. G of m, okay, right off the bat, G of m, that's supposed to be an x value. Isn't m a y value, though? Doesn't really fit. F of k. Okay, we can do f of k. Look, f of k right here is equal to m. G of k. Oh, we just did that. G of k is equal to m. If we add them together, would that be 2 m's? Yeah. Isn't m plus m 2m? C was the right answer then. That one's really nasty. That's a hard question to kind of wrap your head around because you almost have to just kind of like mess around with the 4 answers until you get one that kind of fits. Make sense? Okay, here's a graph of tan. It's really straightforward. It just wants to know the asymptotes. Which of the 4 following things there is the best way of telling you where the asymptotes are? Where's the first asymptote? Where is this asymptote right here? Yeah, half of pi. Right, pi over 2. And then where's the next asymptote? Where's the next asymptote? 3 halves of pi. Right, because this is pi, that's 2 pi. So this is at 1.5 pi. So how far is it from pi over 2 to 3 pi over 2? 1 pi, yeah, the difference between them is 1 pi. So which one of these 4 answers best shows you where those asymptotes are? Let's do the first one. Is it at plus or minus n pi? Well, that means that it would be at pi, 2 pi, 3 pi, 4 pi, 5 pi. That's not where our asymptotes are. It's not this one either. It's got to be one of these two. But this one right here says your first asymptote's at pi over 2, and then every pi over 2 you get another asymptote. But it's not every pi over 2 you get an asymptote, because here's pi over 2, here's the next pi over 2, but there's not an asymptote there. So the best answer here is D. Pi over 2 is your first asymptote, and then every pi in either direction you get another. These are the worst. They're going to give you a picture of a graph. They're going to make a numeric response, and they're going to say, what are the A, B, C, and D values on the graph? Like, literally, they give you nothing but a picture, and they want to know what the A, B, C, D values. Now, this one here only wants B, but just to go through the motions, I'd like to do all 4 of them if we can. So let's start off with the A value. What is this A on a sine graph? Like, what does it control? What does it do to a graph, the value in front of sine? It makes it taller. It controls its amplitude. So let's try to figure out how tall this graph is. It looks like it gets as high as 7 and as low as 1. What's the amplitude of a graph that runs from a 1 to a 7? What's the amplitude of a graph that runs from 1 to 7? Not 6. 3. The total distance is 6, but we want to know how much up and down it goes. So it must go up 3 and down 3. That makes sense? The total distance from 1 to 7 is 6. This is why kids hate trig sometimes. It's like, there's no work to this. That seems to be the middle here. It looks like it goes up 3 and down 3. So my leading coefficient is 3 sine. Where's the middle of a sine graph normally? Like, where does the middle of this graph normally run through? 0, yeah. But that's not where the middle of this graph runs through. Where's the middle of this graph run through? 4. So the D value has to be plus 4 way the heck over there. Makes sense? That's how we managed to get slid all the way up to a 4 here. Now, this graph also has a few more issues to it. Which way does a sine graph normally start? Sine graphs normally go up before going back down again. Do you guys see how this graph right here is actually going down before going back up again? How do I get it to, rather than go up first, go down first? I don't want this graph to look like this. I'm actually trying to flip it over. So how do I flip it that way? Negative would work. Why don't we make it -3? See how that -3 would then flip the graph head over heels? So that rather than beginning by going up, like normally it would go up first, right? Let's have it go down. Okay, well I got another issue. Normally it starts right here. Normally it would start here, but it's clearly been slid over a little ways. How far over has this graph been slid? That's pi over 2. That's 3 pi over 2. What's halfway between pi over 2 and 3 pi over 2? Pi. This graph has been slid over pi, which means that it needs to go theta minus pi to slide it over a little ways. Okay, none of those were what the actual question wanted, though. I just want to do those just for practice. Did those 3 make sense? The 3 explains why the graph goes from a 1 to 7, because 1 to 7 is 6, but half is up, half is down, so amplitude of 3. The negative helps make it so the graph can flip head over heels so that it goes down first, not up first. The plus 4 indicates that this graph has been slid up by 4 units. And then this minus pi right here helps slide the graph over pi units, because it normally should start here and go up, but it's actually starting here and going down. Last thing we got to figure out, though, is our period. This guy right here helps us figure out how much squish compression factor there is. What's normally the period of a sine graph? 2 pi. A sine graph normally has a period of 2 pi. We need to figure out what the period of this graph is. So I'm going to start right here. This starts at pi, and it ends at, let's see, 13, 14 over 2, so 7 pi. How far is it from pi to 7 pi? 6 pi. So hopefully you guys would agree with me. The period of this graph is now 6 pi. Is that clear? What's happened to this graph? Has it been squished in or pulled out? Pulled out. But by what factor? How do you turn a 2 pi into a 6 pi? 3 times pulled out. Does that make sense? You got to pull this graph out 3 times as much. Awesome, you got it. So this value right here, the one that needs to go right in front of it here, this b value that I have right here, needs to be 1/3, because the 1/3 would pull it outwards 3 times as much. So to answer this question here, the value of b would have been 0.33. But I've seen questions before where they ask you what a, b, c, and d happen to be. Things along those lines. I guess you can't really do the pi. You can't put pi into a numeric response value. But we were now able to look at this graph and figure out what its coordinates are. So one more time from the top here. The 3 made it 3 times bigger, taller in that direction, which is why it can go from a 1 to a 7, a span of 6. Right? Half up, half down. The negative flipped it upside down, so the graph started going downwards first. The minus pi is because you slid the graph over so that it starts over here at pi. The plus 4 is because the graph has been moved up 4. The middle of the graph is at 4, not at 0. And then the 1/3 is how you make it 3 times pulled out, like an accordion getting pulled out. So not 3. If you use the number 3 itself, it would squish it in. Make sense? Let's try some more. I think this is just the best way to go right now, by the way, is just, I need to show you some examples of how you might get assessed. Okay, there's some statements here. You've got some random arbitrary graphs. So the first one is an f graph is an a sine b theta, And then the next one is a k sine b theta minus c. Okay, here's what makes these ones suck. Is like you don't know what a, b, and c happen to be. Like they're just completely arbitrary. So let's just roughly talk about what would happen. On this graph right here, you have a sine graph. What does a sine graph normally look like? Well, it normally looks roughly like this. What would this a value do to the graph? What does this leading coefficient do to a sine graph? Yeah, so it makes it so that it goes as high as a and as low as negative a. I don't know how tall or short it is, but it goes from a to negative a. What does this b value do to the graph? Yeah, you're right. Squishes it or pulls it out, depending on what that value is. So I'm not even sure what I can write here because either this graph is getting squished in or it's getting pulled out. I'm not really sure which way it is, but that's what that b value does. Fair enough? This is our first one. So I'll just do f of theta here. I'll write a different one down later. Then we want g of theta. What would g of theta look like? Well, it has the same thing. It's got a sine graph again. Only now it has a k value. How is that different from a? It's not really. It gets as high as k and as low as negative k. I don't know what that number is again, but I know that it makes it, taller. What would this b value do to it? By the exact same thing as this one here, right? That b value is either going to squish it in or pull it out. I don't actually know which one it's going to do, but it's the same thing as the last one. What does this minus c in brackets do? Slides it over. Now, I don't know how far it's been slid over, but really this whole thing right here actually has to get moved over a certain amount here. Okay, so hopefully you kind of have a rough idea in your head of what these graphs look like. This is going to be a regular sine graph that's been pulled up and stretched somehow. This graph right here is the same graph, but it's been pulled up a different amount. I don't know how much it's been pulled up, but I know it's a different amount. It's also been accordioned this way, but however much it gets accordioned in the horizontal direction is the same amount as this graph, but it's also been slid over. So now let's walk through the four answers. Do both graphs have a period equal to b? Okay, let's talk through that. What's normally the period of a graph? Well, normally the graph is 2 pi. It's normally the period of a graph. But whatever that b value is, I have to then divide it by b. That's what the period is going to be. So is the period going to be b itself? No, it's going to be 2 pi divided by whatever b is. So if b is 2, it's pi. If b is 1, it's 2 pi. So that's actually not true. They don't have a period equal to b. They have a period equal to 2 pi divided by whatever that b value is. So is that. The y-intercept of the g of x graph is a minus k units lower than the y-intercept of f of x. Oh boy. Okay. Well, let's take a look at this. Here's the y-intercept of f of x right here. Where would the y-intercept of this graph be? I guess it would be somewhere down here. I'm going to agree that from here down to here is definitely lower. But I think I'm just kind of arbitrarily figuring out where it is from here to here. I don't think that I know that it's exactly a minus k units because there's also this, how the graph got slid over a little bit. I don't really know how that slide's going to affect things. So it may be, but I don't really know that that one for sure is true. So I'm going to come back to that one later. The theta intercepts of g of x are c units to the right of the intercepts of the last graph. Actually, that one's true, isn't it? Because here the intercepts would have been here, and here, and here, and here. And then this graph would have been here, and here, and here, and here. But you slid them over by an unknown value. Aren't they c units to the right by sliding them that way? So actually, this one I do know for sure to be true. Let's walk through the last one just because. the y-intercept of g of x is g of theta is k. Well, k is way up here. I'm fairly certain the y-intercept was actually going to be way down here at the bottom, so that doesn't seem to make sense. Let's confirm the other one, though. The y-intercept of this guy is a. Hang on, I know where the y-intercept of this one's going to be. Isn't it going to be at 0 regardless? Because when it starts at 0 and you stretch it upwards, it's still at 0. So I know for sure this one's out. Is it will follow that? You're probably going to find that in this section here, you know how I talk about like my 3 stages of understanding? That jump from level 2 to 3, though, is the hardest one. Because all of the questions I've given you here have been so varied. Like, there's no similarities between them. There's just a whole bunch of randomness between them all. I don't know what you're going to get assessed on. So I'm trying to prep you for anything I can think of. So let me do a summary of what we've talked about now so far. And I'll give you guys some time to work on some assignments. The 2 main things I need you to know are the unit circle and graphs, and how they relate to each other. How the idea of going around a circle relates to the same concept as a graph. And ideally, you should be able to relate the 2 things to each other. The most recent questions here, though, are, do you know what these graphs look like? Do you know the general properties of a sine graph, a cosine graph, plus then tan, cotan, secant, and cosecant, right? And then know how to squish them or move them around. Okay. Further to that, then can you also solve them for angles and kind of piece all these things